think you went without recording of the voice line. Oh no, start on. Okay. It's okay. Sorry. I was too excited. Yes, square. So mass times velocity squared, right? Divided by what? There is no hint on the board. No. Kinetic energy. Mass, yes. Mass, velocity squared, divided by how many? Adding again. Right. Nice. Okay. Okay, let's thank you for it. Thank you. Right? Yeah. Let's continue our fun journey. Good. So here is your. Now you're on recording. Okay. Please evaluate a little further. Like, how kinetic energy looks as function of momentum, and how does it look like in the quantum world? Like if kinetic energy is operating.
Is that just the Hamiltonian operator, or would I be wrong?
Hamiltonian operator is kinetic plus potential.
Kinetic plus potential.
Kinetic plus potential.
Okay.
And we started writing down kinetic equals mv squared.
Okay.
But if you know that momentum is mv, can we rewrite it in terms of
yeah, but I mean, this one's v squared and that one's just mv though.
All right, square p.
Oh.
Divide by mass.
Oh my gosh. My algebra skills are gonna suck here.
and then you do my square as well.
Oh yeah.
Oh, you're also at the left hand.
Yeah.
So we have 2 to 9% in this class. Roll backwards with yes. Yes.
I'm trying to figure out. Do you just divide by? You can divide by m here, can't you? Just by 1m. Well, you really can't divide by 1m, can you?
Yes.
Oh, you can. Oh.
Wait.
Happy? Close?
Let's try over again. You up to here, you did everything correct.
Okay, so
So-
I'll just get rid of this.
So I like this one.
Okay.
And then you can solve for v squared
Oh.
and then plug it in.
Oh. Yeah, you're right. Oh.
Okay. And then plug it into the expression
Oh.
that was prompted to us by fun.
Oh.
By 2. Then we can cancel something.
You can cancel the m, can't you?
Yes.
So then it's just p squared over
How many gaps?
no, it's,
Keep going, keep
Oh, yeah?
going.
yeah, and then divide by two.
But not this way. Divide by divide will be multiply, but it's
Oh.
both it's like
One half,
of p squared.
yeah.
Let's think why at once. Yes, yes. What she's not over, we can think a little bit more.
Okay.
Now, an equation that I don't understand, I don't know, but I strongly recommend for your own conscious to memorize and be able to answer in the middle of the night. It's maybe like if there are 1, 2, 3 basic equations, it is one of them. So, what is momentum operator in the quantum world?
Isn't that already on the board? No, it's completely different.
Yes.
Oh, that's not fun.
It's not an exam you can interact with class.
Anyone have any suggestions for momentum operator?
There's definitely. There's a derivative. Where is a derivative? With respect to d over dx, or a partial over partial x. Yes.
Yeah.
So there's a partial over partial x, and we want the constants to cancel. We need, I think, negative h bar over I or h bar over I, one of the two.
Anything else?
He's looking, okay, I need a better helper.
Well, all right, I'm gonna go ahead and figure it out for sure, but.
Whatever is, we can just put this factor say no, but is a collective energy money. How would you defend this writing and how you would explain it?
Is it just the derivative of the? I was gonna say Hamiltonian operator.
Over space.
Yes.
But momentum.
Mhm.
I'm still under confusion, impression, and enchantment.
Mhm.
It's like on one hand, momentum is a pace of moving forward in time, right?
Mhm.
It's derivative of position over time.
Okay.
And here it is derivative over space.
Mm.
So how come the momentum is derivative over space? It sounds very confusing, very unusual. We discussed it many times in class, but I lived with it for many years and still under impression. So how do you wrap your mind around if you do this equation is correct? What is the ratio?
I'm gonna be honest, I have no idea.
I will be honest, I do not have a good verbal expression, but we can think together.
Okay.
So the quantum particles, electrons are waves.
Yes.
So this like Gaussians are composed of plane waves.
Mm-hmm.
So which oscillations, which plane wave corresponds to higher energy and quicker momentum, more frequent or more shallow?
This one?
Okay.
No.
You know that.
Yeah.
We just you're same as me. You do not know how to express it.
Yeah.
In verbs and in mathematical symbols. So more frequent oscillations corresponds to quicker motion, to higher momentum.
Okay.
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 And when we take a derivative, okay,
of
x dx,
mm-hmm.
we will get this part. We will get momentum up front.
Yep.
Multiplied by this stuff.
Multiplied by the
same function.
Yeah.
So by taking derivative, we extract frequency of oscillations outside of the wave function.
Oh.
Makes sense?
Yeah. Yeah.
Good.
Yeah.
Let's thank to Wyatt for this.
Assume it's your turn next, so.
Assumption is accepted. I hope you're not bored if you feel encouraged, inspired. This look doesn't. I will revenge you for torturing us. We're asking in front of people. So, simple task, relatively simple. So, let's minus I h bar TDX, right? We all accept it. Okay, now let's, and this is T. So let's combine these two things and write the kinetic energy in the quantum terms by plugging operator of momentum into expression for kinetic energy.
So plug this one into this one. Okay.
I do. What? Yes.
Okay.
And then just open brackets, make sure that things are taken care of. We have about 25 minutes to the end of this unlimited pleasure. I times I is minus 1 times 1 times minus 1 is plus, and h bar squared is what it is.
So when I open this, do I have to do?
1/2 is retained,
Yes.
h bar squared is retained, mass is retained, and then minus times minus is plus, but I times I gives minus. Right?
Yeah.
Okay. And let's do one more exercise.
Okay.
So let's plug for particle in a free space. Potential energy is 0. Let's rewrite the evolution operator with this new knowledge. Okay, please join me in cortex. So, let me share how this class was going in previous years. So that we may learn from errors of the previous generations and avoid them. I really like an arrangement with independent projects, and I think audience also like it. But on the other side, it should be the glory of the class should be projected on the whole department. And there are visitors from the department during the final presentation of the projects. Even if I do not invite them explicitly, they will hear and probably come. And some of them are asking tough questions. You have your research advisors, you know their style, you have instructors in other classes, right? So here is the thing that I myself, I wouldn't say failed, but underwatched, and participants of the class underwatched. So after we're done with discussing how the code is working, we all forget about details and think it is a black box that allows us to do great science to explore chemical reactions. Right? But the visitors to the final presentation tell, okay, I don't care about your chemical reactions. Explain me how the code is working. Go to the blackboard and derive equations. Or just like, so watch it, be ready. Even if I will try to protect and hide our final presentation's secret, there will be diffusion, infiltrating, and some questions. So just keep an eye and be ready on addressing these questions. How this code is working? Through application of evolution operator to wave function at each next step. What is evolution operator? How it is connected to Hamiltonian? What is a momentum operator? Right? And now I know that I probably would be a bad salesman and because every time I repeat the same word, level really decreases. And now I will introduce the most important and toughest concept in the class. I was repeating this several times, but I'm doing this one. So at least something important is going to happen right now, right? And this heavy task will be laying on shoulders of James. So be prepared. So I'm going to explain what is a tough task, and then I'm going to erase the board. So through the help and intellectual insight of previous speakers, we represent wave function in discrete space, discretization, position, discretization in time. Now, we know from momentum operator is a derivative of wave function over spatial model. And then the all intermediate speakers, which they all are very available, told us the connection. So to see how wave function behaves, we need to form functions later, and we need to plug their Hamiltonian energy operator that do depend on the momentum operator. So on one hand, you do have a discretized space for wave function. On another is a basic concept. We do have derivative. We do need to establish a numerical representation of momentum operator, which is nothing but derivative. But we need to do it very meticulous, very careful, and make sure that the point is good. So I'm going to erase the board if needed, whoever needs to elaborate things. As you know, what ideas we can figure out efficiency. And then together with James, I will here along with the team, we will try to develop an understanding how to program the operation of derivative in context of this code. To develop something that later on we can plug into kinetic energy, Hamiltonian, into evolution operator, and to the propagation of the wave function. Okay? So even though we proceed to the board, we will raise here. Like this. So do not worry if things are not absolutely perfect. It is a very tough question. Even if you're confident, let's concentrate and try to be creative. Try to answer with your best understanding.
So we are trying to make a derivative that we can use in discrete form. So the only place I know where to start here is forward difference.
Okay.
So if we want to use forward difference, the forward difference for any generic function looks like this. X plus 1, minus xn minus xn. So that's a forward difference. It's
Okay.
basically derivative over discrete interval.
Excellent, and let's put the wave function, right, just to have a notations.
Okay, so we're differentiating wave functions. Okay. In that case, let me replace our, never mind, they'll stay the same. So that's x. We want to be differentiating or differentiating over x, right?
Okay, everyone agrees? Or it's okay? If anyone disagrees or have doubts, do his, because we need to develop understanding. We will not be so much careful about it, but we need to know how the code is working and we need to be able to answer random questions predicted by students. And from the previous years, it was the weakest place of the class. I was coming to final presentations to celebration, thinking that we will just applaud to each other, happy on the part, do that question. Not to me, students. Write an equation, what is your evolution theory? Why it all this progress? What are criteria of convergence? Why do you do the results? Which efforts have you done to prove that results are correct? Which are kind of standard questions. Okay, so I'm going to have no doubts that you will be able to complete everything, but I will win the discussion a little game to my field in sportsman terminology, a little closer to how the code is written. So, I'm not going to say anything new, just bring terminology. So we suppose we do have values of the wave function at point x. Wave function at point x. In wave function at point x. Wave function at point x. And then wave function at point xn, where xn is npts, as we were instructed by. So the wave function is a vector. And we do need to implement this law, and probably there is a limit to x, delta x going to 0. Formal definition.
Yeah, do we want a formal derivative or do we want a forward?
Forward is fine. And so now, do you keep it in your mind? I just need a little more space. If I erase this, okay?
Yeah.
Okay,
No, forward
so
difference.
we need to form a vector that will include d psi dx at point x1, d psi dx at point x2, d psi over dx at point xn. And we need to formulate a matrix by multiplying which or by through row by column on this vector, we will get this answer. Okay. So and then please proceed as you please.
Okay.
Is the question clear? Do you see benefits and necessity to answer this question for the functionality of the code? Right? So in order to propagate the function forward, you need convolution operator, Hamiltonian operator, kinetic energy operator, and finally momentum operator. And it needs to be programmed in the discrete space. If anyone has ideas, want to help, or just give a hint to James, to me, don't hesitate.
Let's put it down here.
Well, we all are tired and looking forward to complete of the meeting. But if some of you have really enormous amount of energy, you should go. You might take a piece of paper and try to do this thing for you. Or just imagine. Okay.
Oh, fuck. So we're assuming all the x's are the same, right?
Yes. All the x are the same, and we can even put the 1 over dx outside of the.
Okay, in that case, I'm just gonna go 1 minus 1, 0, 0, 0, 0. And then
We don't you need to defend it to the class, but yeah, I like very much the direction. So please continue.
0, 1, negative 1, 0, 0, 0.
We are on the threshold of the true discovery.
0, 1, negative 1, 0, 0. I'm just gonna do one more because this is pretty good. Okay, so looks like we have a diagonal of 1s, and the diagonal is flanked by a little bit of a smaller diagonal of negative 1s. So it looks like we got that's a bad matrix bracket. Let me redo that. We got 1, 1, 1, 1, negative 1, negative 1, negative 1, like just flanking the diagonals.
Okay. Yeah, let's appreciate the help of James for the first time. We need to check if everyone appreciates what we do. How do you interpret? Do you believe what is written? How do you interpret? Please do not move because you may need to defend your. You do not believe or have some doubts, just express. If there's some confusions, definition of like what do you see and how do you interpret? It's not a like question of, it's not an exam, it's just
Yeah.
here's a try to understand.
Okay. Well, I'm not really sure what's going on big picture, but we have a matrix times a vector. And the vector,
I think I screwed up. My signs need to flip. My apologies. So negative 1's diagonal flanked by 1's.
Okay.
and then we're multiplying that by 1 over delta x as well, and we're getting a resultant vector. The vector that we're multiplying by is the wave function at different positions.
Do not lose concentration for next 10 minutes. It is a really important thing.
And the resulting vector gets us the change in the wave function at those positions with respect to position.
Good. So now what is the motivation in this picture? Why do we need it? If you have rough idea of why do we need it, please give me a little sign. If you're not sure, if your idea is not so familiar, just give a sign. Is anyone above shaking hand? Is anyone in the solid? Anyway, please try your best. Why do we need to torture James writing this and us to read this? what is the benefit? How does it relate to moving wave functions?
I'm not sure.
You are. So what did I erase before James started putting his discovery on the board?
The evolution operator,
Which is expressed in terms of
time,
and
momentum,
Hamiltonian.
Hamiltonian.
And Hamiltonian is in terms of kinetic energy, and kinetic energy in terms of momentum.
Yes.
So, and momentum is quantum momentum is
Conserved.
yes, but quantum definition quantum momentum is
Are you asking like mathematical?
yes,
Like the operator?
yes.
Yeah, negative I over H bar. Oh shoot. I didn't memorize it.
Just conceptually, we don't need to memorize things conceptually. What is momentum in the quantum world? We discussed it with White,
Oh,
and we found agreement between our views. I also shared with you that I always kind of confused to express it verbally, conceptually. But finally, we found a way. If you remember what we discussed, reproduce or ask him directly because he's a certified expert on
Like px, px e to the negative I h bar, px, or px. Not like close. That was the momentum, and then like quantum space, because it's like operator. Oh, that might have been the operator I was thinking of then.
So let me reproduce. I know that we are going to collapse all at once very soon. I hope that you will not have the next 5 minutes. So a typical example of wave function is a plane wave.
yes.
So we can imagine plane waves that oscillate with frequent oscillations and shallow oscillations.
Yeah.
Which one of them corresponds to higher energy, higher momentum, and higher kinetic energy?
The one that's moving faster,
Okay.
more
And
oscillations.
if you have as like sine with momentum times x or exponential I px, right?
Mm-hmm.
How to extract momentum from the power of exponential to the front?
Derivative.
Yes. So what is the quantum operator of derivative?
The the derivative with
Should I ask to get this
the
answer?
derivative with respect to position.
Is a momentum.
Yes.
So in order to formulate the evolutionary operator of Hamiltonian kinetic energy, we need operator of
Derivative.
momentum and derivative.
Yes.
So what's the big picture? Why Jack is developing a operator of derivative?
To get momentum.
Yes, and to get kinetic energy and Hamiltonian and evolution operator.
Okay. Yeah.
But we need to do it all in discretized space that was introduced to us by Emma, right? I think we will need to go over it when we meet next time in the lab. But we hope we are developing rough ideas. So now, do you have any more questions? Do you want to give tough time to James?
What is the matrix?
So this matrix, basically, the only point this matrix serves is to take a bunch of differences. But can I, I'm just gonna write it.
Yes.
So the result of this matrix here is just basically expressing each of those. Each of those elements in that vector as, you can just think of that vector as this vector here that's going to be side of x2 minus side x1 over delta x. The next one is going to be side x3 minus side x2 over delta x. So
And then we go down
Oh.
all the way until we have x to the n, or sine of x of n minus sine x n minus. Over double x. So basically, that's a bunch of math algebra for we're taking a bunch of differences.
Yeah.
With the common by rule. We're just expressing their differences as one and negative one. So for the first part, we only need x2 and x1. So that means we only want the negative version of x1 added to the positive version of x2 divided by delta x to get a first part. And then we move down here, we shift the negative 1 and 1 over a spot to get x2 and x3. Slap it over there, shift it over again, and then we repeat for however many elements in our discretized wave function vector to get the vector composed of derivatives. They're basically like coordinates.
Okay, so we're taking a bunch of derivatives
We're taking
at different
derivatives
points. Okay, yeah, that makes sense.
Accepted?
Yeah.
And thank James for so, in a few remaining minutes, I will do a demonstration so that we establish connection between discovery and defense, like James, with actual code. So let me share screen once again. And so last time we looked on the script together with either Spencer or Wyatt. Spencer, right? So we stopped at this line 178, right? So psi2 is just a string of values, but g tau should be our evolution operator, right? So let's scroll back and see where the evolution operator is defined. Tau, tau, g tau, come here. Yes. So exponential matrix, tau, h bar, hem. Hem is not a food. It is Hamiltonian 2, right? So Hamiltonian 2 is defined by px, let's skip this g, px times px divided by two masses. Exactly what we find here. And now to make this code running, we need to find where px is defined. So we have px by one method. We are not going to define, to describe the whole definition, which is postponed. And we have second way of px method 3. So we have two variables that are thought to be related to what James described to us. Now I'm going to the command line, maybe open new figure and type mesh imaginary of px3. So please follow me on doing this little experiment. And now I admit the hardest question was, toughest question was already completed by James. But now it is maybe Kaiden who will teach us what this diagram is showing. So everyone, please follow me and do this. Just mesh imaginary px3. And then the word will be given to Kaiden to teach us what it is. walk through and see that you enjoy this. So talk to each other. Yeah. And we are looking forward to hear from guidance how to interpret this. The way how this programmed is crazy. It will not help any of us to understand what it is. It's really just to look at the figure and divide it. Just our goal is to bring quantum to the kindergarten.
Okay.
Just explain in simple words. Just what do you see?
There seems to be a function that splits down and up, sort of kind of instantaneously, and then back out to flat.
Okay, okay, good. So it is an object, a data set.
Yep.
How many elements are in this data set? What is the structure of this data?
There's 200 data points.
Is everyone agrees with Kaiden, or we want to argue with him? How many data
200.
points are stored in the PXV? Like if I type size PX3, what do I get?
Two.
Which means
There is 2.
what's a 200 by 200?
Matrix.
Arithmetics.
4.
2 by 2 is 4, 100 by 100 is 10,000.
Yeah,
So
40,000.
40,000. So it's 40,000 data points, right? Or is matrix 200 by 200.
Mhm.
Keep going, keep going. Most of the values are,
Most of them are 0.
others are either
1 or -1.
oh,
Oh, it's the diagonal matrix.
yes.
That should be.
So comment. I don't know how to express it by words. Just
So it's just doing the difference between the next wave function at a certain position and the last wave function at our position we want, and it's spitting out our wave function in another position.
so it is a matrix that corresponds to momentum or to the derivative over x, right?
Yep.
Exactly as was introduced by James, by
Yep.
having positive and negative values along main diagonal.
Yeah.
And notice when we were putting it, you are doing imagine, right?
Yeah.
Because in the definition of momentum, it is derivative times negative phi, right?
Yeah.
So does it look like Code and James are going?
Yeah.
Right? So summarize, if you please.
So what we're seeing is what is displayed on the board, which is our derivative of our wave function at each wave function at a different position.
At each point of space.
Yep. And so we're seeing a bunch of zeros everywhere because it's only factoring in the 2 positions of our wave function.
Something nearest neighbors.
Yep.
Okay. And it gives us an operator, quantum operator of momentum, right?
Yeah.
And when we meet next time in this place for these purposes, we are going to take square of this matrix for momentum squared and put it as a kinetic energy, right?
Yeah.
And to give a kinetic energy operator, right?
Mm-hmm.
So now we do have matrices, but we will treat them as variables and compose kinetic energy, Hamiltonian, evolution operator, and then use it to propagate wave function. Okay?
Okay.
But this is a key part of the whole code. How to define a momentum, because the rest is standard definition. Okay?
Mhm.
Many thanks to all of you for agreeing to speak and explain things instead of me. I will not be able to stand and talk for 2 hours. So thanks to everyone. Little, as a favor and benefit to me, please show us film. Yes. Yeah. Meeting is dismissed. Everyone is welcome to disappear. I'm just short of words. Well, we need to put here like Planck constant imaginary unit, basically a matrix represents an operator. Each operator is including differential operators in discrete space is represented by a matrix. So it is a matrix of momentum operators.
So they're all equal to
Yes, and then I think you should have a weekend off from coworks. I may think if it is a miss in the program, but let's maybe keep it this way.
Yeah.
Yeah.
Oh.
Before, you know, I'm gonna you might be right, but you
Right. It's not about you, right?
whether you find better, but it's better good errors if you send it to a print by a need to print, and I'm not very comfortable at the moment. Thank you, James.
Yep.
Thank you, everyone. I don't know, probably tired and exhausted, but I think it is so